Hello everyone, I'm Dmitry Petrov. I'm going to talk about data versioning in machine learning. We'll talk about ML processes, why ML is special in terms of processes. We will talk about data versioning, reproducibility, and workflows. But let's first introduce myself. Right now, I'm building a startup in San Francisco. We basically build tools for data scientists. Before that, I worked at Microsoft. I was data scientist at Microsoft for like almost 5 years. And before I worked at academia, I have done some researches related with machine learning as well. And also, I started working. My first project with Python was in 2004, I think. So I started using Python from version 2.2. For many years, I quit from Python, and now I started again because all data stack usually based on Python today. And in one of my works, so reference to the previous talk, in one of my work, I was a data scientist with on-call duties, and you can take a look at my Twitter, which is fullstackml. So it's reference to the last talk again. So first, let's think what makes machine learning special. When we work on machine learning project, we usually have two different kind of set of tools for versioning code and versioning data. We versioning code by Git as usual, right? It's a good practice. But the data lives separately. And it is a very usual case when you have dozens of versions of your models, graphs, and etc., etc. These files have usually no connection with your code, and people tend to use meaningful names for data files. And it seems to work until you really need a model which was built in the previous week. And then you try to check out your code. You see that code is here, but data files, it's not clear which one is related to your code file, or it can be opposite. You have a model, you know this is a model, this is a file that I need, but I don't really know what exact code I use. And Git in this situation doesn't really help, just because you have a separate tools for that. The thing become even worse if you work in a team. Like a small, 1 second. Sometimes you need to revert your model because there is some issues in production, for example, and or you need to transfer some of your job to a colleague, and it's again you have to do files separately, data separately, and it creates a lot of different disruption in your team. And it seems a little bit strange because we use the best practices, and we know that, right? We use Git, we store our files, and for some reason it still doesn't work. And the question is why? And to answer the question, you need to stop back and think not about the tool. You should think about workflow you use and even methodologies that you use. And today, many companies, especially large companies, which work with data for many years, they realize that data science is different from software engineering, as software was different from hardware design. And instead of trying adopting the software engineering tools to data science, you should think like what is actually needed for data science, what we should change in the workflow, should we change our methodologies. And this is actually not easy to do, because it took us about 20 years to build great methodology and software and tools for software development. We moved from waterfall processes to agile in terms of methodologies. We created Git distributed version control system instead of like huge monolithical configuration management systems. And we invented continuous integration, continuous delivery, and etc., unit testing, and a lot of good things which are supposed to help us, but in some circumstances do not really help. And so large company realized this problem, and they and many of big companies have built internal, which is usually called data science platforms. You probably know that like Uber has his own platform. I work with one of those platforms when I work at Microsoft. Netflix has own platform. Some companies are building this platform and selling for other companies. But we need to understand what concept they use, what is important in data science projects. And there are a few artifacts. First, this platform are operating by experiments, not by code and not by commits. Experiments means code and data. And also, the process, machine learning process is metrics driven, and usually platforms assign metrics to experiments. So it helps you in navigating and in communicating in the team. And some of the platforms support more advanced scenarios, like reproducibility. Reproducibility actually is not advanced, it's a must-have, I would say, for any platform. And machine learning pipelines. And the process itself is different as well. So comparing to software engineering, the process we have trials and errors, right? We can try like 10 different ideas, and only one of those will work at very best. So first of all, I am talking about kind of more mature ML project, right? When you're starting a project from scratch, you probably don't have such kind of problem. And we see these good practices in large companies, and we decided to make these practices available for everyone. So we built an open source project. It's basically open source data science platform. We call it Data Version Control at dvco.org. We are trying to build a platform, a data science platform, on top of open source stack. We took Git as a foundation for this technology, and we basically extend Git by additional commands, by data files, by metrics, by pipelines, and reproducibility, and other typical for data science platform things. So yeah, we use a concept of experiments as a commit and branch, but it contains code plus data. We manage data separately from code, which means you have a separate remote for code, like for example GitHub, and separate remotes for data. It might be S3, it might be like Google Cloud, it might be just a separate machine with SSH access, for example. So this tool is optimized for large data files, which means in a gigabyte range, from 1 to 100 GB. And yeah, it supports metrics, pipelines, and it covers reproducibility. So you can define commands, and the tool
can help you reproduce this command. Or I can define a command on my machine, transfer your repository, and you will be able to reproduce the machine. Or instead of reproducing, you can sync my data through some data remote. So let's talk about data files first. If you probably heard about GitLFS. This is a way how you can work with data files with Git. So there is a tool which supports large data files, but usually people try GitLFS in machine learning projects, and usually they quit from GitLFS just because it does not support large data files as a data scientist needs. So there is a limitation. Only file has to be less than 2 gigabytes. If you have more than 2 or 3 files, it creates some additional performance issue. And what is important in a usual data science platform is a garbage collector for data files, because when you iterate on experiments 100 times, you create 100 intermediate data sets, you create 100 models, and probably 300 different kind of plots. Most likely you'll stuck with a space issue in your local machine, or you probably don't even need as much experiments on your cloud. And GitLFS does not support like your cloud, so you have to work with only like a limited amount of services for GitLFS specifically. So with our approach, you just install a tool, and then in any Git repository you have you can add data files. Like in this example, you just say dvc add and some binary file, and now you have a file in your repository. But what does it mean to have a file in your repository? Because we don't want to push data to Git directly, right? Or even indirectly. Instead, we are pushing meta files. So you can see like git status command. It shows that an image.zip.dvc file was created. This is a file, meta file. And it modifies git ignore. Git ignore, we need this modification just because we don't want to track the actual file, image.zip file. So the tool does everything for you, and you just need to commit these changes. And this information will be available in your repository. So you can push the repository. Your colleagues can sync data set, or not data set, the repository, and she will see that a data file was created. It does not necessarily mean that she will see the data file. It's a separate story. But at least she will see the fact that the file was connected. And yeah, the changes have to be committed, of course. To sync data, you need to create a remote. And this is a similar concept to the concept of Git remotes. You just create a remote, specify a protocol like here, like S3, and then your bucket. And then just simply push your data. After data is uploaded, your colleague can download data the same way as you push the data. So she should use dvc pool with the same repository and get the same data set. This is how you can create, you can train a model in your machine and transfer this model to your colleague. Another important question is optimization of this process. When you work on a scale of dozens of gigabytes, probably each of your checkout is going to take a while, right? So if you need to copy like 20 gigabytes of data, even with a good hardware, it will take probably a minute or even more. And you probably don't want to wait for a minute for each checkout. So the tool optimizes this process. It based on hard links, and the tool never copy data again. Once file was created, no matter how, it's done. So it will never create a copy. Everything based on hard links. There are a few more optimization techniques like ref links for some modern file system. Also, we compute checksum, mostly for reproducibility. And checksum, again, we do not compute checksum twice because it's still, it's again quite heavy operation. So as a result of this optimization, even if you do checkout with a few hundreds of gigabytes, it takes you just a second to do the checkout because there are no copy of no data copies. So let's talk briefly about pipelines. Pipeline is kind of important concept, but it doesn't mean that you need like a pipeline of in a separate step. You can have just a pipeline in one command, like your Jupyter notebook, for example, which takes some input and provides some output. Or you may have a more complicated pipeline when you take data, take raw data, do some transformation, then do feature extractions and modeling, then evaluation of the model. And the tool gives you ability to define the pipeline. There is a command when you can specify input and output, and so the command you'd like to run. And this is a way how you can create a dependency graph, right? DAG. It works. The tool runs command, and again it modifies meta files. So everything on the tool based on the meta files, and all the meta files goes to your repository. This is a way how you collaborate and communicate with colleagues. So in this simple example, one file was created like images, which is a directory as a result of underhiving the file. So, and reproducibility. It doesn't matter how many steps you have in your pipeline. It doesn't matter how complicated your pipeline. It might be just a straight line. It might be some hierarchy. We have a way to reproduce your pipeline, and it's especially important when you work with multiple stages. Because the tool can track dependency, what was changed, what has to be rebuilt, what we can ignore rebuilding, and it helps you iterate faster on your experiments. So, and the last thing is workflow. This is a usual workflow in software engineering. It is called DVC, Git flow, right? When you have just one master or some branch, and you create a feature branch and then merge it back. Sometimes you may have a few kind of master branch, like a master or production, development, etc., etc. But in software engineering, it works in the same way. You just create feature, you develop feature, and you merge feature. And usually in software engineering, you don't fail. Actually, it's a bit more complicated question. You can fail in terms of quality of work. You can fail in terms of time you've spent. But usually still feature will be delivered. And in data science, the process is a little bit different. Because you can come up with a few ideas, and only one of those might work, or only one of those will produce you the best result.
And this is an example of 3 ideas that you come up with. In 2 of those ideas, you made like additional steps, and only one of the idea was merged into a master branch. And why do you need? It sounds like a complicated workflow, right? Comparing to a usual software development workflow, but first it reflects the nature of data science better, and the second, this is a way how you can scale your work in a team. One guy can work in the first idea, the second guy can work on the second idea, and the third on the third, and Git as a foundation can help you collaborate by all of those results. And there are a few tricks which are that important in data science workflow, and one of those, usually you need to jump back to your previous idea, to your previous experiments, and when you jump back, you usually need to create a new branch. So don't do just git checkout something. Usually you need to do git checkout something and create branch right away, because you are going to be working on starting some work from this place. And in data science, sometimes it's important to keep track of your failed experiments. It can be important for several reasons. For example, you come up with some idea, you try that, it didn't work, and you think, all right, it didn't work because I did something wrong. Let's keep it, and later I can continue this work, or I can transfer this to some of my colleagues. And sometimes it's important to keep failed experiment, because I'd like to show to everybody, I have tried that, please don't spend time on this idea. It didn't work. So, and it's important to keep these branches not only on your machine, not only on your local machine, but push them to a central repository that you use. And yeah, and sometimes you don't need some of experiment, just clean them up and don't spend resources on this. So what is, yeah, there are a couple more scenarios how this kind of tool can be used. One of those scenarios is just a replacement of Git LFS when you need a file backend on S3 or on your some other servers. Some companies use the tool to kind of a protocol for communication between data scientists and engineers who is responsible for deployment. Because they need a consistency for data, for rollbacks, and etc. And the new feature that we recently introduced is experimentation on HDFS and Apache Spark. So, which basically means all the things that we discuss you can use on HDFS cluster. So, which means no local machine. Local machine is used only for tracking meta information, but not data. So, data lives on the cluster. It's very important for people who work usually in a large company with a large data set. They spend a lot of time for data preparation, and it's very important to experiment in such kind of environment. And so the question is, when do you need such kind of platforms? Some people don't use any platforms. They're happy with their regular tools, and based on our experience, you need a tool, you need a data science platform or some similar tool when you work in a team. It helps you on collaborating in your team, because otherwise you have to create you have to reinvent basically some basic principles. You have to create ad hoc scripts. And a platform, a platform unifies this process. Platform helps when you work on a project for a long period of time. For example, you have a project, let's say, which runs for more than 1 year, right? So this is basically, you are communicating with yourself in the future, right? You're creating a better infrastructure, better better tools for yourself in 1 month, in half a year, and 1 year. And so we believe it's very important to have open source data science platforms because it will help to work on more complicated open source machine learning projects. Today there are a lot of open source machine learning projects, and usually they are not kind of a long-running project. It's like someone built something, published on GitHub, and that's pretty much it. And we need a project. With a huge community, with a good community, with evolving data set, with evolving models, and data science platform is a way how to support these projects. So thank you. Please visit the tool website, dvc.org. There is a discussion forum, pretty active issue tracker in the GitHub page. And don't hesitate to start the repository. It's an easy way to contribute to the project. There is a lot of activity in the last month in the repository. A lot of people, companies start using the tool. And yeah, please take a look. And now I'm ready for your questions. Thank you.
Yeah, thanks for this introduction. There's a question right away.
Hey, thanks for the interesting talk. I was also recently visiting your website and found the project quite interesting. What I really wonder, what is the unification criteria here? Because there are projects like Quilt, which more like focus on data duplication and data versioning, or there's a model called DATMO, no public. Where what should one use? So what, of course, you are working for DVC, but what is your view towards what is the unique criteria of what you makes the best solution? So DVC.
Mm-hmm. Yeah, and what was the first one?
There's Quilt and DATMO, just to name some. And in the scientific space,
yes.
I think there is.
Yes.
Yeah. Okay.
Yes, right. So, so what we are doing is data science platform, and our focus is supporting the workflow and not just versioning files. And for example, if you're talking about Quilt, it's a data versioning solution, right? You have a library which, when you can use the library to push data, to pull data, to update your data set, and this is the basic use case, right? Our focus is workflow, and data versioning is a part of the workflow. This is the first. This is regarding the Quilt. If you're talking about general, our focus is hands-on data scientists. We don't want to build solution which handle like some of the solution handle just a few gigabyte data set, and they say this is what data scientists need because they use notebooks and simple scenarios. We are targeting pretty advanced scenarios with dozens of gigabytes, with a few steps in an experiment. And we do not build a Python library as many other solutions. So our tool is a command line tool which can be used with pretty much any language, like Python, R, Spark, whatever, and all from the above.
Thank you for the wonderful talk. One thing that happens in the real world with data is that sometimes the shape of your data changes over time. You might get additional fields in a JSON payload, that sort of thing, and it makes it difficult, or if not impossible, to roll back to a different version of a model that does not have any notion of the shape of future data. is there anything in the tool that allows you to set like a flag or something saying, at this point forward, our data now has, fits this schema versus the old schema, so do not roll back past this point?
Yeah, actually, so we do not care about schemas. What we do care is file version and file checksums. What does it mean? If one of your data file was updated, the tool will know that this is what happened, and the next reproducibility step will probably have some issues, most likely, right? If you change data set without modifying code. So we do not care about schemas. It has to be resolved on a higher level and kind of on application level, right? It highly depends on your domain, problem, and et cetera, et cetera.
More questions?
Hi. I'm a bit worried about merge conflicts. Do you ever run into any of these? So there's all these branches being created by different people, but if I use the same file name as someone else and overwrite their data, what happens? Yeah, it's an interesting question. So merge, as I said, we create meta files, right? And most of the job is done by meta files. And when you do merge, you need to resolve issues with meta files merge. It's not about data files. We do not merge data files and don't even try to do this. So yeah, you just solve the conflict on the meta file level, and
is there anything also upcoming, or do you consider something like deduplication or data lineage, something like adding a Merkle structure or something like that? Because I know from very mature data science projects, which like have terabytes or even petabytes of data, in order to do something like back testing and so, I think even with your framework, if there's a training set which is only a few gigabytes, rolling back and forth between data, and or like this case where you have duplicated data sets and multiple repos, as a company you want to have this kind of lineage, right? That you deduplicate and see what went where and where does it come from. Is there something, do you consider adding some feature like that? I mean, a little bit leads into this what also blockchain provides, right? But in the long run, I think data science would also benefit from that a lot.
If you're talking about duplication of data, right, or row of data, then no. It is something which has to be defined on application level, right? It depends on problem.
But also for like data sets which are mutating a lot, so not event data, so like, I don't know, order databases or business backend databases.
Yeah. So yeah, I got the question. So there are several scenarios. First is, for example, databases. When you usually when you build a model, you need kind of some version from the database, right? You need to run some query, and based on this query, you do your analytics or machine learning, right? So this is kind of a separation line between online system and between a modeling system. And when you run query, you take data, then you start your analytical machine learning project. When you need to upload data, it has to happen again. But our system does not care about this thing, right? If you integrate the system into your online system, it is going to be kind of a different scenario. Yeah, but the system does not interact with online solution. And this is actually this design decision. So we need to separate system from data engineers, from system for machine learning people, from analytics, because requirements are absolutely different. So.
All right, so before we thank Dmitry again, I would like to remind you of your karma once again, and please take the stuff with you that you brought. And then we will reconvene after the coffee break. Thanks, Dima, for the nice talk. Thank you.